right, so let's see what happens today. So as you can see from the title, this is a very ambitious undertaking, and I'm really excited about this opportunity. And let's just see how far we can get. Have any one of you ever tried to meditate? Any meditation exercises? Okay, wow. Okay. Yeah. So one of the techniques in meditation is to imagine what nothingness looks like or feels like. Okay, it's kind of difficult to do. It's I'm not sure, depending on which technique of meditation you follow, but this is one of them. And this is really something that is difficult to imagine. So something that doesn't have any properties, any attributes, anything, just nothing. Okay, so I wouldn't expect you to really, but some of you may try. It's a kind of interesting feeling. You can kind of get a feeling of what absolutely nothing, non-existent would feel like. So we'll try. It doesn't matter whether you can get to the state or not, but let's try to start with that, and then imagine now that we take this nothingness and put it in a box. Okay, so we kind of define some kind of box, and we try to put nothingness into a box. Okay, now the question is, we now have something. Obviously, nothing in the box is something. But the question is, and this is a surprisingly profound question in science, is that where did this thing, this something came from? Did it come from the nothingness inside it? Or is it, so let's call it a one, okay? So because it's already something, it's an object, let's call it a one. So the question is, where does this entity, something, came from? Did it come from the nothingness inside the box, or did it come from the box that we used to put this nothing inside? Any feeling, any feedback? What do you think? Any ideas? Any opinions?
I think that box is more important.
Okay.
We need a box and put it in the box. Like our intention is important.
Right. Anybody thinks here that we counted the nothingness as one, as opposed to counting the box that we used to put the nothingness in? Any? So to me, I agree. I tend to agree with you. I tend to agree that we just counted the box, okay, not the nothingness. However, modern science would categorically disagree with you. Okay, the entirety of modern science is built on the opposite assumption. So this is what is called the Zermelo-Fraenkel set theory. Okay, this is, as is written on Wikipedia, and it's absolutely correct. This is the most common foundation of mathematics. This is foundation of all mathematics. Okay, this is what used to build the entire mathematical apparatus that we are working with. And the thing is that the very basic of numbers that we are using is based on the idea that if you take absolutely nothing, an empty set, okay, then you take some kind of symbol that you call brackets, and then you put this nothingness, the empty set, inside the bracket, you can call it a one, okay? But the important thing is that the bracket here doesn't really do any job. It doesn't carry any weight. It's kind of weightless. You can apply this bracket as many times as you like. So you actually constructed one from the nothingness. It's kind of, you created something from nothing. Okay, you kind of use this bracket, but you don't really, you ignore it. You ignore that you use the bracket. you can apply this bracket. It's kind of saying that, okay, we use the box, but now to create two, you use the same box. So you keep putting box in the box in the box, but you each time use the same box. And you can do it indefinitely because the box doesn't have any meaning. What does carry a weight, all right, is that how many empty sets did we actually count, right? And this was something that was obviously this was formulated by the founders of modern mathematics, Ernst Zermelo, Abraham Frankel, and John von Neumann. These are absolutely geniuses that created all of modern mathematics and computer science. Now, these are axioms. This is really the axiomatic set theory. So it's not something that they found, it's something that they established. But the reality is that this is a sort of creation theory. This is creation story. So it's very much like the Bible, right? So it's a story of how you create something from nothing. This is exactly what it's a metaphysical declaration of how do you actually create something from nothing. And then once you solve this problem, because it's really hard problem in science, how did something appear from nothingness, okay? And once you solve this, then you can build on it just any amount of complex logic, and but you need to start with something. So it's exactly like the Bible. So this is actually a fragment from a 2,000-year-old piece of Bible. It's perfectly readable. I can show off my knowledge of Hebrew. So it says, "Bereshit bara Elohim et hashamayim ve'et haaretz, ve'yomar Elohim yeh or ve'yeh or." So, in translating in English, in the beginning God created heaven and the earth. Okay, so this is it has a very similar structure. And then that God said, "Let there be light," and there was light. It's an axiomatic system. So you would think that this is very different, right? So this was math, this was logic. But what is this? This is just saying that God created this, God created that. But over the past 2,000 years, people built astonishingly complex logical systems based on this axiomatic basis, foundations of how something is created from nothing. So basically, to a little bit illustrate this, if modern scientists asks God, how did he do it? How did he actually manage to create the universe? The answer is kind of, you take nothing, you put it in a box, and oh, you have voila, you have a universe. This is what the modern axiomatic system of mathematics is based on. And of course, we went through these creation stories. We have a long history of creating creation stories. So this is one of them. Sounds kind of funny to us today, I guess, for all of you. Earth standing on, it's funny, right? But it's not that funny because people saw exactly the structure in nature. It's actually quite often because these turtles, they bury into mud and then they sleep there during the dry season. And then when the rain starts, they come out and they carry this earth on their back. And so people who saw this, it made a lot of sense to them. And so they took their personal experience as axioms of how the world works. And this is because what we do as humans is we experiment. It's a trial and error. It's all based on personal experience. We try to do stuff, we see how it works, and then we build these stories, we build these interpretations and extrapolations based on our personal experience. This is how we build our theories. And this is something, once we build a complicated theory, we very quickly forget where we started. We kind of assume that everything underneath, all the layers underneath, they are rock solid, because we kind of have this tendency to forget about the axioms that we started from. So to illustrate this further, let's ask a few surprising questions. So what is the meter? Somebody knows what the meter is? How do we measure distance? Like what is distance? What is space?
It's distance traveled by light in some set time. I don't remember what time, but it's speed of light times some time.
To measure distance, we measure time.
Well, it all has history. So it all has history. We try to, we first measured in feet, and then we measured in arms, and then we measured in this and measured in that. So this particular meter is 1/10,000th of the distance between the pole and the equator along the Greenwich meridian. Okay, it's a particular thing that compares to something that is one measure of the planet Earth. But the point here is that it's random, it's convenience, okay, and it compares to something that is comparable to the human scale, right? And the only way for us to measure something in meters is simply to compare any length to this standard meter that is stored in some place in France, okay, in Paris. Now it is correct that now we have a different standard, so that we have some kind of number of some distance that the light flies during a certain number of nanoseconds or whatever. But the origin of this, and it's very practical, is that we took one like piece of metal, okay, we cut it to certain lengths that we completely arbitrarily decided that this will be a unit of length, and then any time that we want to measure distance, we just take and compare this to this piece of metal that somebody cut. The same thing with kilograms. Do you know what 1 kilogram is? It's it has some arbitrary definition for sure. We want to be accurate, but essentially it's just a piece of metal that is sitting in somewhere in museum, and we all go and compare any weight. We have a weight, we put this piece of metal on one side, we put any other objects on the other side, and this is how we compare. So these are all very arbitrary things. What makes things worse, that we don't understand what space is. And what makes things even more terrible, in my view, is that we don't understand what mass is. We just don't know. Does anybody understand what mass is? How objects acquire their masses? Does anybody know what space is? I'm hoping that somebody will raise a hand, but you will be kind of, it's a difficult thing to define. Now, let's look at where we are throughout, so we can kind of define the scale of different sizes, right? We can look at all the different scales of lengths. So talking about the length, right? So we can, this is 1 meter, right? And so we can look inwards, and we can go through all of these different scales. You have the cells, and we have the molecules, and the atoms, and the nuclei, and the proton, and quark, and all of these things. And then going the opposite direction, we get the Earth, and the sun, and the galaxies, and everything. And we have in total like 10 to the power of 36, or maybe a bit more, depending how you count, of different scales. But very remarkably and quite surprisingly, we are exactly in the center of this scale of different of this range of different scales, right? So we have kind of inwards and outwards. We have similar number of scales, not exactly the same, but suspiciously we are suspiciously in the center of it all. If we are looking at the masses, it's even more remarkable. If you take the mass of the sun and you multiply it by a mass of a proton and you take a square root, you get the average mass of a human being. So this is kind of this is kind of should be suspicious. Okay, I'm not saying exactly. Maybe it's coincidence, maybe. But if you think about this, and we'll come back to this a little bit later, but I will just say what is a little bit similar, I feel, is that imagine that you are standing on the surface of the Earth. So what is looks always at the same distance from you, always? Any idea? So imagine you are standing on the surface of the planet, right? And you look around. Is there something that may look familiar to this situation? Okay, so the answer that I'm looking for is it's kind of very similar to the way horizon is, right? So if you are standing on this surface of the Earth, horizon is always kind of, it's very far, right? But it's the same distance forward as the distance backwards. And it's always the same distance from you. It doesn't matter where you go, it kind of, the distance to the horizon follows. So just keep it in mind. We'll kind of get back to this point a little bit later. And then, so I was actually hoping that somebody will say, when we were here, somebody would say, I know what distance is, okay? Or I know what weight is, because then I would show you this, and this is kind of a collection of random, I mean, these are very serious people. These are world-leading physicists, and they argue about things like how many dimensions do we have? Do we have 3 dimensions and time, or do we have time 3 dimensions of time, or do we have 10 dimensions, or do we have 26 dimensions, or do we have only 1 dimension? There is a theory, and here is 14 dimensions. Are we living in a black hole? This guy says that time doesn't exist. What is going on? These are leading scientists. We don't even know how many dimensions we have. What are we talking? What do we actually know? So this is kind of cool. Okay, so I'm making a very abrupt switch to artificial intelligence. I'm leaving you a cliffhanger, but I will get back to this. So my point with all of these slides is that we kind of have an issue a little bit about what we really know about the world we live in. We have certain axioms, certain assumptions that we made, and we built some very sophisticated worldview based on these assumptions. But it appears these assumptions are not really perfect. They are not rock solid. There are some issues with them. Okay, and now we are developed technologically. We developed all these incredible technological capabilities, and we are building kind of brains, AI, that we don't fully control. And the way that we train these thinking machines is by showing them lots of examples, right? So what we do in AI is that we have lots of different aspects of certain situations, and we show them. How many of you have experience of training AI models? So, okay, fantastic. Yeah. Does anybody have experience of training multimodal AI systems where you show not just one kind of, not just images, but simultaneously you show images and text and video. This is what is called multimodal AI systems. Anybody? Okay, fantastic. So this is kind of the cutting edge. This is foundational models. But generally, you either kind of show one type of data, or you can use any number of different types of data that you show to the model. It's kind of trial and error. It's the same. It's basically this. Okay, that's what you do. This is how you train AI models. You show them many examples of what they need to achieve. You have some loss function, getting the toy inside the box. And then after they repeat it a billion times, they know exactly how to classify and how to find, how to match the toys to the holes in the box. This is what AI models do. However, being very clever, these AI models develop a certain worldview. They develop a certain very sophisticated algebraic structure inside that is able to that kind of understands what is going on. They understand the world in a certain way. And so there are many tutorials on YouTube that explain exactly how this happens. But this is basically they're building this algebraic vector space inside the model or inside the brains of this AI model through adjusting all these different weights and parameters. And this is, so if anybody didn't see it yet, I don't know, there's this one particular series of tutorials by 3 blue, 1 brown is absolutely fantastic. It's just explain it extremely well. How these vector spaces are kind of forming inside, particularly with transformers. So a result of this is one particular, it's called Google Earth Embeddings model. These are a foundational model for Earth observation, which is the technical side of discussion today. And what they take, they have all of the Sentinels, the European Space Agency data, which are different, essentially different modalities. It's exactly like you would have text and pictures and videos, and so you have all these different modalities that you put them together and you feed them to the model, and the model is trying to make sense of it all. And what it ends up with is what is called 64-dimensional vectors, right? So this is a 64-dimensional hypersphere. So you can imagine it as a vector on a sphere, but only in very high dimensions, that basically combines all of these types of data. And for every pixel on the surface of the Earth, it creates this 64-dimensional vector that represents all of the information that has been fed about this pixel. And this is just very information-rich data structure that can then produce a lot of answers. So you can then simply touch some very simple layer of the network and start asking it questions. You can ask about the morphology of the terrain. You can ask about weather. You can ask about the surface classes, crop types, if it's agriculture, types of forest, types of urban environment, etc. So it's kind of a data type that contains all of this information together. Yeah. Okay. So I'll switch back. So what I want to say is that this creates inside the model an understanding of reality that we don't really control. So first, we don't really control what exactly this model understands about the world. This is one. The second, this is the first time that this model does not adhere to the axioms that we assume to ourselves. So all of these axioms that we assume ourselves will do math do not apply to this model. It doesn't care about our axioms. Okay, it builds its own mathematics, right? And the result of this is something like this. So this is already 2 years old. Okay, this is a video generating pirate ships and a cup of coffee. Okay, and what is extraordinary about this is a fluid mechanics. I'll play it again. Yeah. So this is a fluid mechanics that we don't understand. We don't have the models that are able to reproduce this. This is physics that this model understood that we don't. And the reason that this model understood all of this physics is because it doesn't care about our assumptions about the world. It doesn't care about our understanding of the world. It made its own assumptions, it made its own axioms, and it built its own algebraic structure that we don't really understand. But this model's physics is better than our physics. This is quite significant. Okay. Okay, so now I'm going to kind of talk a few slides about how do we actually work with models? How do we actually, what the models actually do for us? So the model has inside it some understanding of reality, some understanding of the real world. And this reality has many different projections. And so obviously this is just a little 3D printed toy, and it has 2 orthogonal projections. And the question is, so let's say that I give it this projection, is it possible for the model to predict this? Okay, and the thing is that they are orthogonal. Okay, so there's no mathematical formula that will allow you to calculate this from this. It's not some kind of interpolation. There's no kind of you cannot use a formula to calculate this from this. The only way that you can actually produce this from this is if you, this is your prompt, let's say, right? And then the model understand that this prompt corresponds to this 3D structure, okay? And then the model is able to reproject, to rotate the structure, and then reproject it and return to you. This would be the output of the inference. So let's now, with this idea, with this picture in mind, I want to finally talk about super resolution, which is my main area of expertise. Because, so I will explain what is going on here. This is a result of a super resolution applied to Sentinel-2 satellite. And so the Sentinel-2 picture comes at 10 meter per pixel resolution. So imagine kind of the pixels that are, I don't know, twice or bigger than this room, like very big pixels. And then this is the ground truth, right? This is the picture produced by very high resolution Maxar, whatever satellite. So the question is, can you reliably reconstruct this from this? And just a few short years ago, the answer would be categorically no, you cannot do it, okay? Because you convert each pixel here into 100 pixels here. So how is it possible? Where the information comes from? How can you calculate this from this? It's impossible. But again, I'll go one slide back and say, this is exactly the same situation as here. The point is not that this is calculated from this, because this is impossible to do. But the point is that the model is able to recognize, reconstruct this 3D structure from this, and then reproject it and produce a representation of the image that is high resolution. So this is just another example. So you can see that there's a, how can this structure be reconstructed from this mess? But it can. So I'm just showing for illustration. This is just, it's actually very simple in terms of the architecture. The network is very simple. but this is just the technical description. The point is, so the point is that it's all about this thing here. The understanding of the reality that the model has built. It's all what is called about the prior, about the weights of the model. So I'm going to just contrast it with kind of traditional signal and image processing, which affects our, this is what people that, whoever works with AI kind of needs to understand how it is different from traditional image processing. So in traditional processing, the image goes through long list of different reprojections and reconstructions. So it's a very complicated, this is a pipeline of image processing of European Space Agency. So you have all of these levels of processing, you have the decompression, you have radiometric correction, you have atmospheric calibration, compensation, resampling, reprojection, all of this stuff, denoising, etc. However, in all of this stages, processing stages, it is a process of reprocessing where the next stage is calculated from the previous stage. This is very different from this, where you actually, the model has an extraordinarily strong prior of what reality actually is, and then it projects this image onto this reality, and then it reprojects this reality into a new representation domain. So again, to explain this, you have the stage of training where you actually build this prior. You essentially make the model to kind of build for itself some understanding of reality. And then in inference, a lot of the time people think that this is what you do, but that's not what you do, right? So this is a very important thing to understand. You don't calculate the output from the input. This is not how it works. The way it works is that you have this model of reality, then you project the input onto this model of reality, and then you reconstruct what the real object or image is inside the model, and then you reproject it into a different representation domain. So this distinction is really important in terms of understanding how AI models work and what they can or cannot do. Now, the same process, it's exactly the same process, the same model, same process is either you translate from Chinese to English, I don't know, you translate text to video, you produce songs from prompts, you want to convert a book into a movie. It's a reprojection of some understanding of reality that the model has achieved. Okay, so it contains this phenomenal stage of the model actually projecting your prompt onto its understanding of reality. Okay, so SAR to optical, just for Lydia. And then finally, Sentinel-2 to super resolution. It's all exactly the same. It's exactly the same process. Now, what is remarkable, what is, I think, kind of, I would say, the most, for me, is the most important slide in this presentation, is that it turns out that regardless what you do, you tend to converge to the same algebraic structure. Okay, and this is something that was not really expected. It's something that people discovered. Is that regardless what you do, regardless whether you learn language models, or you learn images or video or SAR data, you eventually converge to the same algebraic structure. This is absolutely phenomenal result. And this is because there's actual reality there underneath it all, underneath all of these data bits and pieces and all of this different things that we measure, right? Underneath it all, there is actual physical reality. And these models, they actually learn it. They build algebraic structure inside them that represents the structural reality. So I invite you to read some of this paper. So this is a paper that I published half a year ago, where I try to explain this idea. I try to actually explain how these models converge to a common latent representation of reality. And kind of the cherry on the cake, and this is something that I'm exploring right now, is that you see this structure, this twisted helix here that you see. It's not accidental, but it's work in progress. I will not go too much into this. So now let me to finish off a little bit return to this particular point and talk about super resolution again, because I find it's very interesting. So you have all of these different scales, and even looking at these pictures, right, you kind of see how we perceive these different scales. There's a presumption in science. So if you look at science throughout the centuries, is we build better machines, we look closer, we zoom in, we see new structure, and we presume that now we're almost there. We're almost there to find the fundamental building blocks, like the fundamental Lego parts that would allow us to explain everything. We have this assumption that smaller is simpler. If we dig deeper, we look closer, really close, we'll find these fundamental pieces. We call them elementary particles that will explain everything, that would explain the complexity, right? So even looking at the images, you see that the further in we go, like it's become connected balls, then it's just a kind of structure of balls. And eventually we have only balls, and then like we're almost there. It's almost we almost found the Lego, okay? But the reality is strikingly different. The reality is that we dig in, we zoom in, but it doesn't become simpler at all, like not even close, right? So this particular bacteria, it hunts this other bacteria. It doesn't have any brain, it doesn't have neurons, it's a single cell, right? But it has all the capabilities. It hunts, it lives its life, it mates, it does, it does all the things that we do without all of these parts that we think that give us these capabilities. So we go another 5 orders of magnitude deeper, and this is molecular biology. It's inside the cell. It's a I forgot its name. It's a system that delivers a protein inside the cell from the nucleus to the outer edges of a cell, right? This is like phenomenally complex structures. It doesn't become simpler at all. And finally, this is a simulation of a single proton, right? So proton is not a ball. It's an extraordinarily complex system that doesn't show any signs of being simpler than any other structure that is larger than this. So there's absolutely no reason to assume that smaller parts are more elementary and simpler. So where this brings us to is this is nothing particularly new, but this is a fractal structure, right? So the further we zoom, the more structure emerges. And the interpretation is this is something that you can simulate yourself. There's like formulas all over the internet, you simulate it. It's kind of classical stuff. But the interpretation of this is that, okay, there's a new structure that's been generated. We generate more structure, we go deeper and deeper, and we generate new structure. But the reality is not that. So the reality is more like this. Do you know Game of Life? Does anybody know Game of Life? Yeah. So have you seen this? This is a game of life that is simulated inside game of life that's simulated inside game of life. So it's a system that is not infinitely kind of complex. It's a system that is actually very simple, but it's a scale periodic. It's scale periodic. It means that the outer itself is the inner itself. So if you, the deeper you go inside, you come from the outside. It's the same. So the scales are the same. It's a scale. It's scale periodic. It's not scale infinite. It's not a linear progression of scales. It's the same scale. So this is finally brings me to this. There's this idea that you have. So you know Fourier transform.
Yeah.
Have anybody heard of fractional to Fourier transform? So you can kind of have a transform which is part of. So you have a signal domain and you have a spectral domain, frequency domain. Okay, but you can do so. Fourier transform is kind of is a full transform, but you can do only part of this transform. And it turns out that you can prove mathematically that fractional Fourier transform is actually scale shift. It's a zoom operation. So basically what you get is you have this cycle where you start with a signal domain, okay? And then you zoom in until you arrive at quarter turn, you arrive at Fourier transform. Then you continue to zoom, you arrive at the reversed image, and then you continue to zoom, you arrive at minus Fourier transform, and then you continue to zoom, and you arrive at the original signal. So the interesting thing, this sounds complicated, right? But the reality is that you can demonstrate it immediately with a single magnifying glass, and I invite you to try. So you start like this, you put it close to your eye, and you move away, and you will see the image scaling. You will see you see bigger image. It zooms in, okay? But the moment that you arrive at the focal point, so the distance between the lens and UI becomes a focal length, distance of the lens, you will see Fourier transform of the everything kind of blues. You will see Fourier transform. This is not exact. You need to have a special lens, but you will see close to this. And then you continue to zoom out, and you will see the inverse. So what you can do, just because I have a short hand, but what you can do with yourself, and I invite you to try it, is you go from here, you go here from one focal length, and you get here at two focal lengths at full extent of your arm. So basically what this shows is that the zoom operation is it's a rotation in the representation space. And there's a whole theory called Heisman-Weyl representation theory in quantum mechanics that basically formalizes this. And so, so this is something that I'm working on right now. I'm trying to prove that basically scale shifts and zoom operations are actually equivalent to fractional Fourier transform. So if anybody is interested to this, I'm happy to to share. This is still work in progress. And okay, final thought is that essentially what we call these different sciences, right? Biology, chemistry, physics, these are all different languages essentially to describe reality. They are representation domains of the same reality, and in the same way it's kind of rotation in the representation space, and this is, I find it quite interesting. So thank you.
It's very important and interesting to understand how it works. Because we are used to build classical models to understand phenomena, that we build the models and we analyze the models to understand what's happening. This is completely different approach. This is very difficult to understand. Have you any questions? Yeah.
So you presented the idea of emptiness, like something was created of emptiness. So if we go very deep, like we zoom in, and there is something that it has something
There
inside.
is nothing, not something.
Right. Exactly. So we have at the very bottom of everything, we have nothing, probably. And yet it's something because it's within some box or structure or so.
So I want to
Is
be,
it also what
In my understanding that you said that if we have nothing, we add nothing, we have something.
so you can, so I mean, I'm trying to avoid going into full on into metaphysics and philosophy. I'm trying to, the whole message of this presentation is that all we have is the reality that we are in, and we need to stick with that. Okay, this is very important. We need to base all of our deduction and assumptions based on real subjective experience. Okay, so regarding nothingness is a very helpful thought experiment, right? But we have absolutely no experience of nothingness. Okay, we have no experience of non-existence, and so while this is kind of a contrastive thought experiment, okay, good for meditation, okay, but we cannot say that if we zoom, there is nothing, because we don't have this experience. Nobody has ever seen nothingness, okay, and so I would avoid, proposing something like that. So the whole point is that we are living in this reality, and we need to try as much as possible to stick to the reality that we experience. Yes.
Yeah.
Maybe a more practical question. You.
Go ahead.
Not philosophical.
Yeah.
Sorry. Regarding larger numbers and numbers of modalities. When you showed the example of the 64-dimensional structure, and the hope is to start including more and more modalities observing the same reality. If a classical problem that people run into when they start trying to analyze large dimensional structures is the curse of dimensionality, that basically Euclidean distance breaks down at higher order dimensional structures, such that everything kind of exists on the outer surface.
Yes.
You run into this problem if you're trying to parameterize, if you're trying to make efficient some model that's got lots of parameters. You can't find two spots that are close to each other that are similar because of this curse of dimensionality and Euclidean distance breaking down. Do you see AI as running into that same problem as well? Or is it maybe going to be a solution for that?
So this model, okay, and this is a very characteristic. This is a very interesting model, and I think you can learn a lot from reading about how this model works. It's I find this is kind of right now is a reference for a very competently trained and executed foundational model, especially in our domain. Okay, so this space is non-Euclidean. This is a 64-dimensional hypersphere, okay, and the fact that all of these vectors are indeed on the surface of the sphere, and they tend to go on the surface of the sphere spontaneously. So you don't need to force them to end up on the surface of the sphere. They seem to converge to the surface of the sphere because they prefer a metric that is not Euclidean. And this says actually something about how we kind of used to Euclidean metric. This is what we used to, but this is not. This is one of the things that what I said earlier, that the way that these models operate, they don't care about what we are used to. That a lot of the time they do their own thing. So this has a cosine similar. This is basically angles between vectors in 64-dimensional hypersphere. Okay, and I actually discussed it with Pavel. Pavel, not here. Yes, we just discussed it a couple of hours ago that if you start actually applying Cartesian Euclidean metric here, you will have a problem. It's really ineffective. So whether 64 is the right number, I don't know. It's maybe you are completely right. Having too many dimensions is a problem. Having too little dimensions is a problem. So you need to find the right balance. But you need to. These models have kind of their own preferences, and these preferences have a lot of sense. So we kind of need to start learning about what these models actually prefer to do, rather than imposing some of our own methodologies. Does it answer? I'm not sure.
Yeah, no, I
Yeah,
think
but
so.
but also continuing this idea, if we are building the classical model, we are building model to explain something which we have defined. Yeah,
That's right. Yes.
yeah. That means that we normally reduce the dimension, reduce a modality, because we want to explain only given phenomena. Yeah.
Exactly.
So these
Yeah,
phenomena are so many, but in the artificial intelligence model, we don't reduce this. Yeah, we
That is
still
absolutely
have
right.
the knowledge about the whole modality of the system, but we use for understanding only some of them. Yeah,
You are
but
absolutely right. Yes.
my problem is another, because I wrote some books about the modeling and the models, but in a classical meaning. It was several years ago. That was nothing about the artificial intelligence. That's we build model based on data. We build some formulas, equation which describe the model. Then we choose some of them. Yeah, but how we will extend the knowledge, because we want to find something new from artificial intelligence, if we will use for science, yeah, to find something new. How it will work, because we will train the model based on the closed set of data. Yeah, how to find something new outside this set. It is possible. That is the sense to build such a model, because if not, a classical model will be enough.
So I completely agree with you. It's a major challenge. Like you made several points, all of them are absolutely correct. So first of all, the dimensionality need to not only include the specific problem that you want to explain, but you need to give the model sufficient capacity, right, to represent its own understanding, modeling of the world with all of its representations. So you need to have all this dimensionality for it to be able to do that. Now, so specifically for this model, okay, we have no idea which modalities and what information it actually stores in the able to predict. It's entirely kind of opportunistic trial and error. So Google Earth, Alpha Earth released it to the public. It's open access, right? And so this embeddings, not the model itself, but the embeddings. And so people can now experiment and see what the application is. What is that this model is able to predict? And this is it's very intentional. So Google wants people to experiment and come back to Google and tell what does the model actually, what it can actually do, because they themselves, they have no idea, right? So I think the approach here, there will be many approaches, I don't know, but one of the simplest approaches that you need to just by trial and error experiment with this model, communicate with it, and at some point, maybe it will tell you what it can do. So
This is by experiments.
That's right. So so for
But
example,
if we are doing some scientific research, if we are starting the scientific, we don't know how many parameters we need to know to describe something or to discover something. Yeah.
yeah.
This can be the infinite number of parameters which influence the phenomena which we are testing. That's how we deal with this problem.
The example that I wanted.
Of the model.
So the example that I wanted to, I think I don't think many people here have experience with this particular model, but probably all of you have experience with ChatGPT, right? So the way that we know what ChatGPT can do for us is by just trying. People try all sorts of things, and for some things ChatGPT is doing phenomenal job, and for some things it fails and does a terrible job, right? But the only way, there's no list of tasks that ChatGPT is good for. People experiment and figure out what it can do. And I think this is the same with this and with a lot of these models. These are models that are extraordinarily powerful, but we don't understand them. We don't understand what they know and what they don't know. The only way that we access their kind of knowledge is by trial and error. And then, you know, the good and bad, like there are all of these examples of how these models are terrible, but there are also clearly, there's a lot of things that they are very good at.
That it's a very optimistic message for us that people are needed. As you said, people are needed.
What maybe it's a very good point to put in the end is that they are different. Okay, they have different type of intelligence, right? But for humans, I don't know whether anybody read Solaris. It's them. I'm sure you. So there's a phrase somewhere there that humans need humans, and this is something that this AI will never replace. Is that humans need other humans, and for that we'll still need humans. That's like this will not replace, but
between will be artificial intelligence.
So exactly like all other machines, all other tools, this is a very sophisticated tool. It also, in my opinion, has the potential to, you know, to become a new species of, you know, at some point to replace us at some point in the future, but not anytime soon.
Okay. A few more questions, Mark. Something to add?
Yeah.
Please.
Yeah, what is the future of Earth observation in machine learning in your opinion? What is the ultimate goal? And also, a second question, do the models that are built, trained in order to solve something should always rely on multimodal features? What's your opinion about it? Third question.
Yeah.
Are they domain foundation models necessary?
Right. All right. So let me try to start with the first. I think the foundational, multimodal foundational models are the future to significant extent, because they have so they have all of this. Okay, so let me where did I have this ideas? Here. Okay, so it's just if your model always sees just one projection of your data, okay, it just has no clue. It's just very limited. It will not be able to rotate, right? If it has two projections, it can already start rotating and producing all of these different output modalities, right? So the more projections you give it, the fuller picture it will, and it actually happens very rapidly. It's not that you have 2-3 modalities, it suddenly see all this diversity and complexity that it cannot see with one projection. So in my opinion, multimodal foundational models are the future. However, having said that, simple tools have, like you have 3D printing machines and all this fancy stuff. You still have screwdrivers because in some situations you have the best tool is the simplest tool, right?
Yeah.
And so dedicated task-specific models absolutely will have a niche. It's not for everybody's running about this general artificial intelligence, right?
Yeah.
So for general artificial intelligence, you will need to have multiple modalities. For some simple tasks, you will definitely have very simple, small, reliable, like rock solid single modality models. There's no doubt about this. And the third question was,
The domain, the foundation models.
so that's what I said. So that's
Yeah.
a single, I wouldn't call them, I mean, it depends on the terminology. I wouldn't call them foundational models because the whole point of foundational models
Is that they
is
are
that
general, right?
you train
But
one model.
domain-specific multimodal,
I think all of the combinations are viable. It really depends on the scenario. I think all of these combinations are totally viable. It just depends on what data you have. One thing is very important to remember is that the more modalities you have, the harder it is to synchronize them. It's like it's to have, for example, with SAR, right? To get matching SAR optical pairs, or even matching hyperspectral, high resolution pairs, this is a major challenge. And so additional modalities come with a lot of complexity. But if you can get them, they tend to do a very good job.
Okay, but this problem, in my opinion, can be solved by statistics. For instance, I give you the example. We did with one of my PhD, but he is not here, my PhD student, that we had only the 2D picture of the regolith particles.
Yes.
But we obtained a 3D model from the statistics because we know how we tested the statistic between the plane figures to 3D figures, and it works very well. Yeah, that's what is I can say relation between statistical approach based on the big set of data to the artificial intelligence approach.
It's exactly the same thing. I mean, AI models
only the tools are different.
Yeah, so AI models are fundamentally statistical machines. They are so it's there's they have some very strong nonlinear structures, okay, that form the statistical.
Nonlinear statistics also exist.
Exactly. This is I kind of my statement would be the opposite. We tend to separate mathematics into all of these different domains: statistics, linear algebra, geometry, this functional, this, that. They are not. That's the same thing. In the end, they are all based. So all of the modern mathematics and non-modern mathematics is based on counting. So all you do is you can write any mathematical statement, every mathematical statement in existence, in terms of set theory, just counting. Right? And this is essentially what Gödel, all this Gödel, you can represent any mathematical structure with just prime numbers. I think but the thing is that it's different languages, like Chinese and English. So one is Chinese is like linear algebra, and English is functional analysis. They are all just different representational domains of the same algebraic structures. And this even, there's a Van-Gram program. There's a big mathematical consortium that has tried to unify all of mathematics into one. They basically show these bridges, how everything is equivalent to something else. So probability theory is part of it, and all of the AI can be described in just a little bit more complicated, but statistical analysis.
Okay. This is
We have some questions
Yes.
from chat,
Yes.
online chat. Okay. Could you talk about the reason for model hallucinations in the context of AI models? Could it be the case that sometimes the model's hallucinations are not mistakes, but the model is uncovering new phenomena we are not aware of yet? If so, how can we tell?
It's a fantastic question. I actually spent quite some time talking about it in the course that I gave about hallucinations. So hallucinations are ubiquitous in classical analysis. Like it's not nothing new. So when you you fit a function, I actually have these slides. I won't open them right now, but or maybe I will. It's because it's very easy to explain visually. Let's say that you have a bunch of points, okay, and then you assume that this is a straight line, okay, but actually it isn't. Or so you made an assumption, you overfit it. So let's say that you can I draw
there
this?
is-
Oh, okay, yeah, perfect. Yeah. But probably
we will try to find. Isaka, potrzebujemy.
Have one here.
No, no.
so. Let's say
Okay.
let's say that you have a sum.
Yes, it's a question from the audience.
Yeah, I know. I know. I moved my laptop.
Okay.
No. I'll know how to do it. So
That we will move
I
the.
just moved it.
Yeah.
I'm happy to answer this because it's a very it's a fantastic question.
Yes, it seems.
They see?
Yeah.
Okay. I just now find the pen that.
Better.
Yeah, it's not quite very well. So let's imagine if is there something that writes?
Joseph, one
Yeah.
sec. That's,
That you will get the better one.
Yes.
please try the black one.
This one is perfect. Yeah.
Okay.
Okay. Fantastic. Okay. So let's imagine you have some linear phenomenon. Okay, and you have a bunch of points. Okay, and
Better now or no?
it's much better. Yes, fantastic. Thank you. Yeah, so and you feed it a polynomial. So this is a linear phenomenon. Okay, and there's a question here. There's a bunch of points that you have that have some error. Right, this is a typical problem. There's no AI, nothing. Okay, and so you decided that you will try polynomial instead of you overfit it, right? And you drew something like this, okay? This is hallucination. It's a very simple phenomenon. It's a mismatch between your assumption and reality. So the models they overfit, okay? They read your prompt and they really try to. So for example, what is a typical problem of hallucination in ChatGPT? Like you ask the model how many how good a ballet dancer Tchaikovsky was. I mean, like something that doesn't make sense, right? So you ask, was the Tchaikovsky a good ballet dancer? Okay. And so the ChatGPT, it really wants to please you. So it tries to satisfy all of your points. So it assumes that, okay, you probably know about Tchaikovsky, so you probably know that he probably was a ballet dancer. So let me try to give an answer that would make sense in the context of the question that the user asked. And so he will say, yes, he was a fantastic ballet dancer, because it tries to overfit your prompt. And so this is exactly the situation that you get. This is the hallucination that you get. And this is a mismatch between the prior and the reality. And this is a very common phenomena outside of AI. Does it explain? I have some really
But we
much
can
better.
have different hallucinations based on that.
So absolutely.
Because this model can have different
Yeah,
slope.
you can also do this. Okay.
Yeah.
So you can do this, and so this would be extreme case of overfitting, right? And this is so this is hallucination.
Can be different.
Yeah, and so the
So is the only way to get a hallucination to ask a question that is wrong in a way? Or are there any, I'm asking,
There is no wrong question.
I'm asking if,
This is not Lufthansa.
I
You know
ask-
this joke about the Lufthansa? Yeah, if you ask Lufthansa about something, then you will have answer. We are Lufthansa, we are asking.
yeah,
There is no wrong question.
so
yes,
I'm interested if maybe whenever we ask AI
yeah.
a question and get a hallucination, does that mean the question itself is asked assuming something that is wrong?
It's misaligned with the prior worldview of the model. So if it's misaligned and it's not able, so what it does is, so essentially it's I'm simplifying a little bit, not by much, but the AI model inside is as a multidimensional manifold, some kind of very complex, like a shape, geometric shape inside, okay? And you give it a prompt that is some kind of collection of points, and then it tries to match, it finds like a DNA. It tries to attach your prompt on some kind of a section of its geometry. This is how they operate, okay? And then essentially what happens is that, you know, that all AI, all large language models, they are trained by just predicting the next word. This is basically all they do, right? And so if it finds the match, it just continues. That's all it does. Okay, it just continues, and this is the output that you get. Now, when let's imagine you gave it something like this, okay, and it doesn't match anything. It doesn't match, okay, and so if it doesn't match, it will try to find some weird place to attach itself, and it will give you a weird answer because it didn't find anywhere to match your request. So this can happen. These hallucinations can happen. It doesn't mean that we overreact when we immediately recognize that it's a hallucination, right? A lot of the time, it still didn't find place to touch. It still didn't give you a weird answer that was a guess, but it got it right, and you didn't notice, right? So a lot of people that use a lot AI for publication, they get some citations, references that are on, and then nobody even cares or notice this, and then it gets published and everything. So a lot of these hallucinations go unnoticed. So the fact that everything makes sense to you doesn't mean that it found the perfect match. But this is the exact source of hallucinations. Now, indeed, going back to the question, some of the time this mismatch would represent genuinely something new to the model, okay? And this model can produce something unexpected. And this something unexpected, in some cases, may actually be something correct and innovative. It's also possible. It's very unlikely, but it's also possible. I would say that relying on the hallucination to produce something like really fundamentally interesting and significantly new, I don't think it's a good idea. Just answering the original question. But this is exactly what hallucinations are.
So in that framework, it should be able to be parameterized and potentially regularized against.
This is exactly right, and they do it. So, for example, ChatGPT, because it is complicated, so they don't. All the earlier AI models had temperature, right? So they had just a slider that you could, and this is exactly like that. They reduce the polynomial. They try to match this thing to the manifold, okay? And you could adjust if you want to have something that is reliable, would not hallucinate, but the answers would be kind of dull. Okay,
That's the right.
there's a trade-off. If you make the temperature high, right, it will produce a really interesting answers, but this is but it will be a high risk of hallucination. But it's the same as us humans, right? If you want to never make any mistakes, you probably will unlikely to say something interesting and significant. If you want to go out there and say some significant things, you will hallucinate. Sometimes you will say nonsense. There's like it's the same as us.
By the regularization, you add the information to the model, extra information. Yeah.
Yeah.
So if you apply regularization. Okay, but in this case, if we will have the ideal models which will fit all these points,
Yeah,
that you will have no hallucination.
but so you can
Because
never.
if we will have reality which is via points, yeah, you said this is a points of reality, these points, yeah, and you will build a model which fits all these points without any errors, yeah.
Yeah, but this is so the reality.
Very difficult to understand.
No, I think I understood. Okay, yeah, okay.
There is a reality point, yeah,
Yes.
and we build a model which fits all these points. There is no space for hallucination.
So
Because
yeah.
that you have the reality here, model here, and this is a hallucination.
So the points never come like this. The points come like there's a mess.
Yeah.
Okay, and then what the model does through training is to find the optimum regularized.
Depends how many dimensions you give to this model.
Yeah.
If the dimension will be equal to the parameters,
Yeah,
it can be ideal. That means that you will have no hallucination.
Sure. Yes.
That is also the good message that in the future we can have the AI without hallucination. But we need to spend plenty of time to train this model. Okay. Okay. Questions? Yeah, more questions, please.
I'm looking from the LLMs, but I wanted to ask a question about the resolution of scaling.
Yeah.
So how does it work in terms of, are we creating information from no information, or so because we are creating more pixels from one pixel, but
Yeah.
I know it's not that simple, but are we creating information from the model, or are we information from your and to ask, so is there a gain of information after the upscaling, or we are having the same information, but we're just kind of extracting it from what we have?
Different projection.
It's a different projection. So imagine again. I don't know. I'll try to see what you see from the window. It's kind of a drawing. Usually, so imagine. I'm trying to see it. Imagine some very distant. You don't see it from the window, but let's try to just use it as a thought experiment. Imagine that you are standing and you see a tree very far away on the horizon. So can you imagine this tree, how it looks from up close? Can you imagine? Okay. So depending on your drawing skills, right, you would be able to draw it, right? This is exactly what super resolution model does. It has experience of seeing this tree from up close, and as long as it can recognize it, okay, as long as it can actually identify, okay, I see there on the horizon just a few pixels, but I'm pretty sure it's a tree. And this is particularly true for Sentinel-2, which is a multispectral data, because it actually can identify, recognize these objects not just by their shape, like a plane or a tree. It can actually identify these objects by their spectral characteristics, by their spectral signature. And so the moment that it knows, okay, I think this is a tree, let me draw a tree, right? So the knowledge, the extra information comes from the prior, from the experience, from the internalized kind of world model that the model has. This is where information comes from.
Okay. I understand.
Okay, thank you.
A follow-up question.
It's a question, yes.
Yeah. How does this training sets like generated for this model? Because the one proof was the low resolution satellite photos.
Yeah.
What was the training set like? What was the high resolution images?
They were generated from. So we took high resolution images of air. There are multiple very large data sets of aerial imagery. And then you need to find matching pairs, and then you go through many steps of harmonization and augmentation. So you basically, you take a relatively still, these are very large data sets, several terabytes, right, of data, but it's still not enough because you need to diversify them. You actually use synthetic augmentation of the data to make them much more diverse. But fundamentally, you still create these pairs, training pairs, exactly like projector result, but basically you have exactly the pairs of Sentinel-2 and the aerial image, but you need to make sure that they are matching exactly both morphologically and spectrally.
Okay. So,